Welcome back and continuing our exploration of diazonium dyes. Before we do the breakdown for the synthesis of trypin blue, let's do the mechanism for the steps in the synthesis of methyl red. So what I'm going to do here is define this species here as, oops, not with that pen, I'm not. H2, get my color. H2NAR. And we'll do the mechanism starting with that. I've got my screen in a bad position here. Sorry. I'm going to reach a little bit. Okay, we got a lone pair on that, but we don't have anything to react it with yet until we draw a nitrite ion reacting with HCl. So what's going on is we're going to make AR attached to N attached, nope, it'll be linear, with a plus charge on the middle nitrogen. That's our goal. To get there, we need to have nitrite ion. And HCl. First step, red first. Protonation. And then the next step would be, well, let's not combine too many steps. You could try, and it would be fine. But I do like to see nitrous acid here. And then you have to protonate it to make it have a better leaving group, water. There's excess HCl here. I didn't indicate it, but any NaNO2 mechanism, there's always excess HCl. So you first have to protonate to make a better leaving group, and then induce it to leave with the lone pair on the oxygen. Not too happy with the way that looks. There. Lone pair comes in between the N and the O, makes a triple bond, and here's our triple bond. Switch to dark blue because that's what color it is in the picture there. And you made water, but we don't need to see water. At this time, the aromatic amine that needs to be diazotized will react with your nitrosyl cation that you just made. That's that N triple bond O. It's called a nitrosyl cation. And you're going to have AR with 2 bonds to H. It's going to have a 4th bond, so it has a plus charge. Hey, didn't we have a name for this blue group? That's an N, it's a nitroso group attached to nitrogen. So it's an N-nitroso intermediate. I don't need to see these words on your test, but sometimes words help you remember things. N-nitroso intermediate. Remember, it had to become an N triple N. Well, you don't have to remember, it's right there. But how do we get there? Clearly the O has to go, and it's nowhere near going when it has 2 bonds to nitrogen. So there will be protonation of that O. There will also be tautomerization to get the double bond to switch positions. We need an acid-base pair to accomplish that. And HCl. It's the conjugate acid of Cl minus. when it's tautomerization, we are combining steps here, aren't we? But it's such a standard mechanism that we do it all at once. There. And you get AR with an N. Nope, not a big R. AR. Still has an H down here. Now has a double bond to nitrogen. And that has an O with an H. It's going to have two H's pretty soon. Plus charge. And it's time to get rid of water. And once again, dehydration. Knowing what we know now and didn't know in Orgo 1, we do know you should protonate it first if it's going to leave. And then make it leave. So protonation first. And then conjugate base makes it leave. With an elimination, triple bond, that will become water. Yeah, both H's are black, aren't they? There's your water. More importantly, we made our Diazonium species. We can just draw it. ARN. That needs to become our dye. How? How does that become our dye? I don't even have a picture of our dye anymore, methyl orange. So we have our nucleophile. We can figure out our methyl orange picture from what we have here. We have N,N-dimethyl-aniline. That's going to attack this thing we have here. And we're going to draw it happening here. And it looks like it's, make it purple. Why not? Do you remember how the attack happens? Why is it important the nucleophile has a lone pair on nitrogen or oxygen? Because that lone pair is the activator towards this electrophilic aromatic substitution. This is the nucleophile. It's resonating in to be a nucleophile, sort of like enolate resonance. Or enamine even. Looks more like enamine, doesn't it? And we're going to get what looks a lot like methyl orange, but it's the unaromatic or non-aromatic version. That's what makes it look like a dye right there. And in the purple, we have a new bond. And how's this thing look? It's going to have double bond there, double bond there. My molecule got flipped upside down. But there it is, upside down. And what about this carbon here? That can't stay like that. That's sp3. It's got an H on it. And that needs to become methyl orange. How does one do that? How do we make methyl orange? Well, any base you have around will do this job. It doesn't take much. Water's fine. Cl- is fine. I'll let you use anything you want, as long as it's one of those two. There's more water than anything with it being the solvent. So water grabs H. Aromaticity is obtained once again. And we've made methyl orange. Let's put an arrow to methyl orange. And we don't have to do the mechanism for tryptophan blue. We just have to do an analysis. So the nucleophile. In the middle, there are no nitrogens attached to the well, this one doesn't count. It's part of the diazonium, but there's nothing that could have made this a nucleophile or this. So this is the electrophile. And our nucleophile, what color do we have for our nucleophiles? I think where were we here? It was red. Let's go find it. So our nucleophile actually has both in here. It has a phenol and an amine. Which one do you think is the participating nucleophile in the mechanism that makes the dye? Well, I just need to remember, nitrogen is much more nucleophilic than oxygen. It resonates more, its electrons are pushier. So I would think in the mechanism, the lone pair is kicking in here, rotating all the way around and coming up here and then attacking the N with that right there. But we don't have to do that mechanism. You just have to analyze what we have. And remember, you have to make the electrophile first. What do you make the electrophile from? I think we have the retro from here. Where did this electrophile come from? There's the E. Here's the E. Here's the nu. And the electrophile came from an NH2 on the benzene. Well, we're going to have an NH2 here and an NH2 here. So that's our pieces. But the electrophile right before it reacts looks like this. And if you're curious what this kind of a molecule is called, it's called a biphenyl. And this biphenyl has methyl here, meta to where they're attached to the two phenols are attached to each other. And we have to have an NH or an N triple N here. I was thinking ahead, it came from an NH2, NH2. One on the left, one on the right. NH2 here, NH2 there. And the nucleophile was the naphthyl species. Naphthyl. I'm looking at the one on the right as a guide. Although they're both the same. Symmetrical dye. One away from the bridgehead, NH2. Oh, can we just call those the alpha and alpha prime positions? Alpha here and alpha prime there. Alpha's one away from the bridgehead in naphthalene. Naphthalene. And to be consistent, the NH2 didn't make it naphthalene. And the phenol didn't make a naphthalene. It's a naphthalene amine and naphthol. And what else we got? We have SO3H, SO3 minus meta to NH2 and meta to OH. And that is our nucleophile. Now, curiously, And for reasons I don't have a great explanation, why is this the nucleophilic position here and not, say, para to the NH2, which would be my favorite? That would be my first guess, but apparently that's not the way it goes. We don't have to know why. You'd think there'd be some steric hindrance issues here nestled between two groups that would be somewhat solved over here, para to the NH2, but they don't go together that way. When you mix these, you get trippin' blue. And this thing, you can buy that. And this thing you can't buy, you have to make it from the appropriate aniline. In this case, would be a biphenyl version of aniline. Wonder what I can do here. We'll see. What was it right before it was N triple N? Let's get rid of the whole thing. And that's it. So you would diazotize that in the forward direction. How did we do that before? You need NaNO2. You need HCl excess AQ. I don't need to see the excess, but I do need to see some reference to water. And I need 0 degrees Celsius. I don't want a phenol over here or over here. And then I just mix these together. Let it warm up to room temperature. Might have to add a base, but you don't need to know that for lecture. And you get your trippin' blue. Now you're wondering why there's so much more detail in these notes than there is actually in the textbook. The very last thing I got to when I was doing the textbook was these diazonium dyes, and circumstances mean that the chapter didn't quite get done. And after that, we don't have chapters. So we'll worry about that when we worry about test 4, because we do have enough information for test 4 material at Moodle. And here we just expanded a little bit on our knowledge of diazonium dyes that was not in the book, and we'll finish it here. Diazonium dyes are called indicators. Indicators often have different colors, in this case at different pHs. So methyl red at pH 3, which is low pH, has a red color. That's where it gets its name. It turns yellow at high pH. This is 4, 5, 6, 7. Yeah. So if pH is above 5, you're yellow. pH is below 5, you are red. So it got its name there. And in the middle, you have this. Methyl orange is, I hate to say it, it's almost the same. It's a bit of a fib me doing this, and I apologize to people that actually published this online. I couldn't find the picture for methyl orange. It's similar. This is not actually 100% true. This is closer to 4 and 5 and 6, 3 and 2. And methyl orange gets its name from the transition color here. These aren't the exact right colors at the end here. And I'm even going to admit this is a bit of a fib. That's a small lie. But the thing I'm trying to get across here is this changes color at a lower pH than this one. because methyl orange has a lower pKa than methyl red. pKa, well, pKa never goes away, does it? Methyl oranges is closer to 4. It's a little lower. And well, sulfonic acid is it's a more electron withdrawing group than a carboxylic acid, which would have inductive effects, lowering the pKa. And we want to know what these things look like after they pick up a proton. So this is the basic form here. These are all the basic form of these 3 diazonium dyes. Oh. And we'll be drawing the acidic forms over here. But one thing you need to know is they protonate similarly to how they were made, in that this nitrogen's lone pair pushes into the ring. Same for this one. And once again, what's lone pairs pushier towards the ring, the N or the O? The answer is always the N. And you need to push towards the nitrogens that are the diazonium nitrogens, both examples. So we're going to pick up a proton, but it happens by way of resonance. I got to resonate all the way to those nitrogens outside the ring and ask or answer this question: which nitrogen, the one that's closer to the resonating nitrogen here or further, which one gets the proton? It's a good question. Look at the mechanism and tell me the answer. This one's going to be C double N. The one that's further away from the resonating nitrogen is the one that protonates. So I'm going to make a comment. Protonate the distal diazonium nitrogen. Okay. Protonate the distal diazonium nitrogen. Yeah. Make it red, make it bold. And that's going to be true for every example. You just leave it there. Distal and proximal are good science words. Distal meaning at a greater distance, and proximal would be the other nitrogen, the one we're not going to put a proton on, the one that's in closer proximity. Love those words. Borrow them from our biology friends. And what we have is methyl orange in its low pH form. It's going to look like this. Acidic form. That's what low pH form means, right? That nitrogen's going to have hydrogen on it, and I think we can do some advanced scouting on short forms. That's the resonator. This ring is not going to change. And in this one, the resonator is over here. This whole thing over here is not going to change. That's going to help a lot. We already have enough to draw. Call it AR double prime. And we didn't finish drawing our molecule here. AR over here, new hydrogen here. That's the one. And I could save even more time. Might be getting a little greedy here. Methyl red and methyl orange have very similar stories. The only difference is the ring that doesn't react in the acid-base reaction. Call that AR prime. We already did. This piece is the same. And we're going to do the mechanism for tryptan blue picking up HCl. I'll redraw the HCl a little closer. And we got to resonate all the way to the diazonium. Quickest way there. Once again, look, mechanism says it's got to be the distal one. Ooh, I'm getting dizzy. We got an O-3S benzene that looks like this now. And across here we have, did I do that right? Oh, no, we don't have this. Hasty. Let's draw the two rings first. Did I draw them? Yeah, that's where I went wrong. And that double bond is here. Double bond to nitrogen up here. And we still have this double bond down here. We have a double bond of nitrogen here, down to a nitrogen here, to AR double prime. And where's the new H? That's the question. New H is there. This is the acidic form of tryptan blue. And I can't remember. I think tryptan blue's acidic form is the blue one. And I don't know the other color. I did not look that up. I apologize. So we've got acid-base behavior. So what do you see in methyl orange? Well, at low pH, you see the acidic form only, which in both methyl orange and methyl red, fibbing aside, I didn't fib about that. The acidic form for both is red. So methyl red is actually named after its acidic form. Methyl orange is named after the transition form. Confusing, I know. So if you have low pH, then you only see this acidic form. If you have very high pH, you see the basic form, which in both methyl orange and methyl red is, got to make this bigger, else yellow is very hard to see. The basic form for both species is yellow. So at high pH, you see yellow for each. At low pH, you see red for each. And in the transition, you see between 3 and 5. At pH 4, you see an orange color. That's how methyl orange got its name. It's the transition color. Now, this one changes color at pH 5. Why? Well, at pH 5, pH equals pKa. And if you remember, whoop, we still got our chubby pen going here. There's this important equation. Blast from the past here. Let's make it look fancy. There you go. pH equals pKa plus the log of the base form over the acid form, and then command shadows. Okay, and what happens is if you have only the base form, you're going to see the color that corresponds to the base form. If you see only the acid form, you see the color that corresponds to the acid form. What happens if you have equal amounts of the base and acid? When these are equal, pH equals what? If you have the same number in the numerator and denominator, you get a ratio of 1. The log of 1 is 0. pH equals pKa. So what happens when you have equal amounts of, visually, when you have equal amounts of red and yellow, what do you see? You see orange. Similarly here, equal amounts of red and yellow at a different pH, you see orange. And whatever the colors would be here, when we had equal amounts, we'd see an intermediate color. Okay, so it's visual actually has numerical connotations, and that is a good spot for us to stop. And we will pick up with a brief amine chapter conclusion, and then we can do a review segment for our test coming up. And I'll see you very soon.